All right. Well, thank you very much, Ken, for being for allowing me to be here, and thank you all for coming to Stanford. Because Stanford has been involved in NMR since the beginning, we thought it might be kind of fun to talk a little bit about the history of MR. So, so how do I do this computer? There. Okay, so a little about me first. So when I graduated in EE, I went to GE's Research and Development Center in upstate New York, and I started playing with solid state physics, which is what I was doing in my prior years, and then got involved in time-of-flight focused ultrasound because that turned out to be an interesting topic. So I got into medical imaging fairly early, and then went to working on CT because the Research and Development Center was starting to work on CT at that time to transition it to the medical systems. So then I went to medical systems in '76 and began to transition the reconstruction algorithms and so on to for the CT product that GE was building. It was a pretty interesting device because instead of taking 4 minutes, it took about 10 seconds to gather data with a fan beam acquisition. And then in 1980 went on to MRI. And so I was there until 1990, and then I came to Stanford where I was recruited to start the radiological sciences lab. So a little bit about what I was doing in Schenectady. This is my breast scanner that was involved in a hospital in Albany, and where there was a number of subjects with breast cancer. And so we were interested to see whether the speed of sound could depict cancers. And I don't know if this, this will, oh, it doesn't show up. Okay. Well, I have a pointing device, which won't work for the 150 online. But anyway, the speed of sound could depict cancers, and that turned out to be very interesting. At the time, my lab back in CR&D had this high-speed interface to the computer center in the CR&D with 1,200 baud. So it was amazingly fast because the typical 300 baud device was pretty slow by comparison. Still very slow. So we'll start with nuclear magnetic resonance. And this guy, Isidore Rabi, was the person that first published and talked about nuclear magnetic resonance in the sense of molecular beam resonance. And I won't go through the details, but by changing the magnetic fields around this molecular beam, he could demonstrate a resonance phenomenon that was being then described by a lot of people who took up this molecular beam resonance and began looking at nuclear magnetic resonance. And so it depends on spin magnetism, where if you have, for example, a proton, a spin 1/2 nucleus, and you put it in a magnetic field, it will align itself with a magnetic moment that is either in a low energy state or a high energy state. And the nice thing about this spin 1/2 system is that by adding some energy, you can cause spins to transition from the low state to the high state, and the energy you have to provide is very precise. It has to be exactly the right amount, and so that's the resonance phenomenon. Now, this is a subtle effect. It's only 16 parts per million difference in a resting state, between these things. So NMR is by its very self extremely small effect, and it is this small effect that has caused an entire universe of interesting science. So a lot of people began to work on this process of NMR, and these two guys, Felix Bloch, who was a chemist at Stanford, and his companion Edward Purcell at Harvard, got the Nobel Prize for this by their very esoteric and detailed research in this process. So we were involved in this from the very early on. We, the Stanford. I actually never met Felix, but I met a number of his lab members when I came to Stanford. So NMR became a ubiquitous laboratory instrument. Everybody had to have one because it was an awesome way of looking at the chemical properties of materials. And so every academic lab and a lot of industrial labs had NMR NMR machines to look at the properties of materials. And because of the interesting way that this resonance was created and probed, you could make interesting ways of looking at different properties of the materials. So now pulse sequences were developed. And many researchers found that these novelties were very exciting and very good science interest. So there was a lot of interest in using this technology to explore different ways of looking at stuff. So this was a typical NMR system in the 50s and 60s. Had an electromagnetic magnet, and initially no gradients or anything else, so they were just static. You could tune the magnetic field because it was an electromagnet, but there was very little imaging stuff involved in it, of course, from the beginning. So these guys, the professor from Stony Brook and from Nottingham, UK, developed imaging. And so they made seminal contributions to the aspect of using NMR in an imaging environment, that is, applying gradients to change the resonant frequency in ways that could be observed using Fourier transforms or other techniques like that. So Paul Lauterbur and Peter Mansfield got the Nobel Prize in the early 2000s, which was quite a long time after their original publications, as you'll see. But I was kind of pleased to be able to be one of the nominators for Paul, who lived down the street, if you will, in upstate New York, and we had collaborated early on. This is Paul Lauterbur's initial paper, and he was using filtered back projection to do the reconstruction, using again the concepts of the resonant frequency depicting space through the use of gradients. And it's interesting when you're the first and you publish a paper. This was his first paper, and it was actually the first paper on NMR imaging. And there are six references in his paper, and none of them are on NMR imaging. They're all on NMR because he was the first. He was the first to publish this, and so it was very exciting to watch this occurrence. So that was Lauterbur, and this was Mansfield from the UK, and he made seminal contributions to, for example, selective excitation and so on. This is how pictures were made back in 1970s and 80s using an overprint on a page. So this is actually an annulus of his object that he was scanning at that time. He also made contributions to echoplanar imaging, which is a mainstay of fMRI and many other techniques like diffusion weighted imaging and so on. But it covers K-space, that is the Fourier transform of the object, in one or several shots, if you will. So it could be very fast. And as a result, it became immediately interesting in cardiac imaging, where you could make movies with time resolution of several hundred milliseconds or so. And Peter built his own system because you couldn't buy one in the early 80s, and introduced shielded gradients, which was a useful thing to diminish eddy current contributions. So there were many NMR contrasts that were possible, as opposed to that in CT, where it's scatter and Compton effects only. Here you had dozens of different ways of using this technique for contrast, and shown here is T1 and T2, for example, which are relaxation mechanisms. So just by changing things like the echo time in a spin echo sequence, you could make amazingly different contrasts that were exciting to radiologists and to other biomedical imaging scientists, because just by the simple process of changing a few parameters in the way that the pulse sequence operated, you could highlight different kinds of contrast, for example, in the brain or other parts of the body. And that, again, as I said, was very exciting. So that was fun. Here's a gradient echo sequence, and that gave you a different kind of contrast that turned out to be very useful for example, bold fMRI. And it was actually a lot of research went into these different kinds of pulse sequences.
Gary, 5 minutes.
Yeah, it'll just be another hour and a half. So this is a guy who also was a neighbor of Stanford, and we saw a lot of him. Erwin Hahn, he developed diffusion weighted imaging. And that turned out to be very interesting because it nicely depicted acute stroke, for example. And so about in the early 80s, manufacturers started building these things because they turned out to be extremely exciting for clinical applications. And so the early NMR people were developing different ways of imaging using very different kinds of concepts that were SNR dependent. So a three-dimensional acquisition turned out to have better signal-noise ratio than the lower dimensionality. And I'll just show a couple of examples. This is one of the first body images made, and it was made by moving a coil around a person's body. So it was a kind of a stupid way to do it, but it took half an hour or so, so not very perfect. But other people began to use multi-dimensional stuff like line imaging, where you could make nice images of grapes and stuff. And the original 2D-FT technique that was developed at GE in Schenectady. And so, again, you could make all kinds of different images. And here's the EPI technique of Mansfield. And this is another depiction of that same device, annular device. So the versatility included different ways of covering K-space using, for example, spiral versus echoplanar. And again, these rapid techniques became very exciting for all kinds of acquisitions. This is one of my grad students in the early 2000s, who you'll hear from later, Christine Law, showing that the spiral technique recovered signal in the frontal orbital areas much better than echoplanar. It continues to be that today. And there are lots of other ways of covering K-space that can do things better, higher resolution or something else. So a lot of papers were published that I won't talk about, but there was a huge amount of research that went into imaging because of all the exciting possibilities. And so here, for example, is the use of Bol and by Seishi Ogawa in 1990, and then by the group from Harvard, and then a group from Medical College of Wisconsin, and that was in 1990 to 1992. And I looked yesterday. It turns out that there are now about 750,000 papers published on fMRI. And I looked at spine imaging in fMRI, and also yesterday, and there are about 600. So there's work to be done. So don't go away and then forget about it. Go off and publish a few thousand or a few thousand papers, please. And functional connectivity became an exciting concept. A whole lot of things were developed. So just a couple words about the lab. It was founded in 1990, and we had a three-part mission, which we continue to do today. Research, education, and collaboration. As Ken said, collaboration is important. And we now have about 13 faculty in the group. And we opened the Lucas Imaging Center in 1992. And I was proud to be able to bring Richard Ernst, who the year before got the Nobel Prize in imaging. And he inaugurated our lab. So he's worked down the street at Varian, and was a close collaborator with a number of us. So just a final word on imaging. Again, this is some work by a grad student of mine in the mid-2010s or so. And what Haysam found is that the spinal cord has a huge amount of off resonance. This is a magnetic field plot, plus or minus 250 hertz. And there's just a huge amount of off resonance. And it turns out that since MR imaging arises from magnetic field changes, that changes of this sort made a huge issue on how to do this imaging in the face of such large off resonance, which occurred because there's a brain, and there's a spinal cord, and then there's a big old torso hanging out, and that makes for magnetic field inhomogeneities. But they overcome that using this big off resonance in the brain and the spinal cord with dynamic imaging techniques that Christine will talk about later. So here's pulse. It turns out that imaging the brain and the spinal cord are quite different from the standpoint of resolution and everything else that you need. So Haysam developed an early pulse sequence, which Christine has been working on since, that does a marvelous job of depicting both the brain and the spinal cord in function. And so here's a few of the publications, and just from Christine, who's in here somewhere. And what I want to point out is that there's a lot of collaborations going on, as Ken said. It's a very collaborative concept with a lot of multi-site studies going on. And here's just a few more of them. And I just want to, again, point out that while Christine is one of them, there's lots of people that are collaborating on this. And that's a very exciting thing, because collaborations are what really make the field blossom. And so, just in summary, MRI evolved within the academic environment, which was very different than the CT environment, which was very proprietary and not open at all. And that openness led to a lot of different developments of techniques, as you've seen, and that allows very rapid, widespread science to be done, but also science that were, in our case, for example, at Stanford, we have a lot of clinical collaborators. Where our lab has 13 faculty, we probably have 15 or so more just collaborators that work on various parts of MR and CT and a few other things that we do. And so MRI is about 5 decades old. Spinal cord imaging is about 1/5 of that. So again, there's still work to be done. We're excited to have you here. Thanks very much for coming. We appreciate you being here and for seeing our awesome history of development in MR, NMR, and so on. The spinal cord community is, as I said, very robust, and take advantage of that for networking trainees. And we hope that you will find this workshop useful. So I'm sorry I'm over time, but. I won't take questions because
Gary will be part of the panel discussions later, so there'll be opportunity for